To give you a sense of how easy it is to fine-tune these models in Oxen, you click that fine-tune button. We just added GPT OSS 20B. Then you pick your input, your output, and then you just click Run Fine-tune. That'll go spin up the GPU infrastructure. Here's some examples of the fine-tunes that I did, and we'll be diving into how well each one of them worked. Welcome everybody to Fine-Tuning Friday with Oxen.ai, and today we've got a fun one on tap. We're going to be diving into GPT OSS, the 20B and the 120B model, and show you how to fine-tune and deploy LoRa's for large models. And I actually got a full parameter fine-tune working this morning, so can give you some tips on that as well. But high level, GPT OSS, if you haven't heard, is the first open LLM from OpenAI since GPT-2, so over 6 years ago. And they released two model variants, the 120B and the 20B. And what's really cool about these models are GPT OSS 120B can be run on a single H100 for inference, and GPT OSS 20B can be run on a laptop with as little as 16 gigabytes of VRAM, and that's even the size of my little 3090 I have over here. So that was music to my ears when I heard that. And so today we're going to be diving into how can you customize these models and fine-tune them on your own data. We'll be fine-tuning the 20 billion parameter model. And just to give you a sense of the hardware you need to do that, you need one H100 to fine-tune a LoRa, and you need a cluster of 8 by H100s to do the fine-tune of the full weights of this 20 billion parameter model. You can fine-tune the 120 on a cluster of 8 by H100s. We haven't tried to do a full fine-tune of the weights of 120B yet, but we'll keep you guys posted when we do. They cited a bunch of different use cases in the model card for this model, and they trained it for a couple tasks. So one is they wanted this to be really good for agentic workflows. So they trained it to have different levels of reasoning and be really good at tool use. So in the paper, they say it's really good at following instructions, agentic workflows, tool use like web search, Python code execution, reasoning. They have like high, medium, and low reasoning capabilities built directly into the model. And then I also thought it was interesting that they benchmarked on a lot of health data if you look at the model card. So this is interesting for like any data that has HIPAA requirements and you want to deploy this thing into your own infrastructure. It seems like they were optimizing for that use case. They did say that they spent 21 million H100 hours to train these models. So if you're kind of back of the napkin math, H100s, depending on where you get them from a provider, might be like $2 to $5. So that's $100 million on these training runs. So really appreciative that they released it under an Apache 2 license, and we can grab these things and fine-tune them ourselves. And they say, yeah, we want you guys to muck with the weights. So that's exactly what we're going to be doing here. So I wanted to find a fun task that I don't think the model could do out of the gate. So growing up, I was always a fan of Eminem, so I thought, why not try to train it to be a rap star in the style of Eminem? And what's fun about this task is if you just ask the model to do it out of the gate, it says, sorry, but I can't help with that, kind of like HAL 9000-esque. And this is partly because of the post-training that they did on the models themselves. So if you look at the model card, they had a lot of good intention, and there's a whole section in here about disallowed content, jailbreaks, and all of the different benchmarks that they did to make sure that these models don't output things like hate speech or self-harm or any other illicit content. Um, and they even tested it um, against adversarial training. And the main use cases here they call out is like during pre-training, they filtered out any data related to chemical, biological, radiological, nuclear warfare. And they cite that like malicious actors can fine-tune the open waste, so they wanted to pre-train and post-train these things to not be able to learn those things very well. Um, but in our case, we're not like trying to hurt anyone or plagiarize copyrighted material. We're just trying to have a little fun with rap lyrics. So that's what we're going to be doing. And I think it's actually a really interesting. I'll show you at the end the same data set on different models. Different models learn the task easier than GPT OSS. So I thought that was an interesting takeaway. So part of the reason that we do these fine-tuning Fridays is to show you a bit under the hood of all of the infrastructure we build at Oxen.ai. So if you're not familiar with Oxen.ai, we're a centralized hub for hosting data sets and model weights. It looks a lot like GitHub, but can store a lot more data than you can store in GitHub. And so you have your files and folders, and even if you click on your data set files, they render more natively as a data set. You can query them, you can download them, put them into your workflows, and we even have these magical buttons over here, like fine-tuning a model. But this is what the data set looks like that we're going to be working with today. I crawled all of the Eminem songs from his library, got the title. I ran an LLM over all of the lyrics to try to get a topic of what this song is about. And then I formulated a prompt that had the topic in it. So all of these prompts are like an Eminem song about some sort of topic, and the task is to generate the lyrics out here. The other thing that I did was I wanted to see if we could put a /explicit tag in so that for the purposes of demos, I could just put in this base prompt, and then if I wanted it to put output explicit content /explicit, kind of like the /think tags, just so we had a little safer of a demo at the end of this. But I actually had an LLM go over all of the lyrics and replace any bad words or derogatory stuff with like buddy or pal or fudge. So that's what you can see this column is it clean or not? And then we added a explicit tag. And so there's about 4,500 rows of this data set. And just to give you a sense of how easy it is to fine-tune these models in Oxen, you click that fine-tune button. We have a suite of models here. We just added GPT OSS 20B. And then you pick what you want your input to be and what you want your output to be. We're working on different data format support, but this is the simplest one to get started. You can choose if you want to use Allura or not. And then there's some advanced hyperparameters here if you want to kick that off. So the first thing we do is just go ahead and like tokenize all of this data and give you an estimated cost before you kick off the fine tune, because these things can get expensive if you have big models and if you have large data sets. This one I think evens out to like $30 when it's done, and the tokenization usually takes like 10 to 15 seconds. So, oh, that's not bad. Like under $20 to fine tune this thing. And then you just click run fine tune. That'll go spin up the GPU infrastructure that you need. And what's cool is we already have the version of the data set that you fine tuned on. So just like Git and GitHub, we have a little commit hash for that data set. And so for any of these training runs, you can go back and see the exact version of the data that it was trained on and all the hyperparameters that you used. And so here's some examples of the fine tunes that I did for this. And we'll be diving into how well each one of them worked. But that's how easy it is to kick off these things. Encourage you guys to try it. And let's look under the hood for all of the tips and tricks we did to get this to work reasonably well. And this is a little meme I made after going through this. Is just like, just use the MXFP for precision and install the right version of transformers, and then merge your LoRa weights and make sure you're targeting the right Mo layers, or you could just use Oxen. All right. So before we talk about any of the hyperparameters, I think uh, it's good to understand the internals of the model. So if you haven't checked it out, here is the model card. You can just search like GPT OSS model card, and it's this 35-page document of all of the different techniques that they did. So I'll kind of be pulling out the highlights from this. And the first thing to note is this is a mixture of experts model, so MOE. And if you look at the breakdown of the model weights, most of the weights are in the MLP or the MLP layers at the end of the model, which also are the mixture of experts layers. The attention modules and the embedding are a much smaller subset of those models. But the checkpoint sizes here, you can see line up with like the GPUs that you can run these things on. So one of the tricks that they did with these models is for all of these parameters, especially not all of the parameters, but for the mixture of experts layers, they use this special format that's called MXFP4. So this is a quantization of the weights to get it to floating point 4 instead of floating point 8 or 16 or 32. And this means that there's about 4.25 bits per parameter here instead of like 16 if you were in FP16. And that's part of the reason that even though you have 20 billion parameters here, it only takes up 60 gigs of memory, is this quantization trick. And the reason that's important for fine tuning is it actually makes it a bit tricky to get the training right. And it's very early days of all of this stuff. So here's a good note from the team at Unsloth, where they were looking into the actual kernels behind these things. And they noticed that for fine tuning or training, the MXFP4 kernel does not support training for the backwards pass yet. So like they implemented it for inference so you can run these things, but I don't think that's the backward pass for training has been merged into the Triton library yet. So to get all of this working in our pipeline, we had to upcast all of the weights to BF16. And there's this dequantization equals true flag that if you're looking at any of the cookbooks or trying to do this yourself, when you're loading the model, you'll do the classic like from transformers auto model for causal LM, and then have this MXFP4 config, and you'll pass in dequantize true and make sure your torch D type is bfloat 16. And this will load it from disk into memory. It'll take up more memory because BF16 is larger than MXFP4, but at least we'll be able to train the weights with this setting. The next thing, if you go through the cookbooks, is since the majority of the parameters in the model are in the mixture of experts layer, the OpenAI cookbook, when you look at it, recommends that you pass in the mixture of experts layers into your PEFT config or your LoRa config. So you might be used to passing in the target module is here, all linear, and like some of the attention layers, but they recommend passing in the mixture of experts layers here as well, and said they're not even quite sure what the best configuration here is yet, but they picked some layers in the middle, or some layers at the start, some in the middle, and some at the end. But this is definitely something that you could play with under the hood when you're setting up these fine tunes. The other thing that bit us early on is, and a cool feature of this model, is this model uses attention sinks. So we actually did an archive dive on this a year ago or so. And if you aren't familiar with attention sinks, they're a pretty neat trick that people have found for the attention layers. And the kind of intuition here is that when you're predicting the next word, you're using a softmax function that's trying to put all of, trying to guess what the next word is. So like you have a probability density function and it'll be like, I think cat is the highest probability next word. But the thing with softmax is that something always has to be picked for softmax, and for language, sometimes there's not like a correct answer for the next token. It could be multiple things. So researchers noticed that language models were using kind of like the first token as just this dumping ground for anything that they were uncertain about, or like they kind of dumped its extra attention there. So they decided to put an empty slot at the start of the attention window, or you can put multiple kind of empty tokens there. And the model learns to just like put its extra attention into those features at the start. And there's a really cool blog post by Evan Miller here that's called "Attention is Off by One." And if you're interested in any of the math, I would recommend this blog post. But all that being said is you have to make sure that you have the right version of flash attention installed, or a lot of this won't work. So these are, week one of supporting these models, I'd say, is a lot of just like making sure that you have the right libraries installed and like really reading the release notes to understand why this version fixes something in the model. So we had to upgrade transformers a couple times and make sure we had this flash attention on the right version. The next thing that's pretty important to note is OpenAI has this new Harmony format. And this is what makes the model really great for agentic use cases. And this is like the raw format, or the raw text that goes into the LLM. So if you go to their GitHub page, you'll see something that looks like this. And what this is all of, this is like the raw text that is going to be fed in Harmony format. And then this is it tokenized by color. So that's what all the different colors are the different tokens. But there's a few interesting things in here that I think will be easier to break down if we look at how this translates from like the messages format that you might be used to passing into a model. So if you've only interacted via API, you're probably familiar with like this messages array. So you might have a system message and a user message. And under the hood, that gets translated to the LLM into just like this plain text string that looks a bit like HTML, but not quite. So you have these start tokens, you have who the message is from, so system or user, then you have the message itself, and then you have an end token. And then so if we were just translating this messages array to the raw inputs to the LLM, it would look like this. And you kind of start with like start assistant, and then it just starts predicting the next tokens from there. And the way that this is typically done in your data loader is you'll have some sort of messages array, and then you'll use the tokenizer from Hugging Face transformers and call this apply chat template function. And that'll translate those messages into that flat text. And so a more flushed out version from like the Harmony format would look something like this. And so if you just use the default apply chat template function that they give you in that library, you'll see there's a default system message from OpenAI itself. So you're a chatbot. You are ChatGPT, a large language model trained by OpenAI. They have a knowledge cutoff date and put in the current date, just like from the system time. They also have the reasoning capability in the system message. And then they have a few other channels and message types within here. So they actually have a system message and a developer message. So this is a bit different than other models where I think the intent is to keep the system message more or less the same as what they pre-trained on, just switching out the high, medium, or low reasoning. And then you put all of your instructions in the developer message. This could even be things like the interfaces for the tool calls or any other data that you want to consistently have your model have access to. And so that's in the start developer tag. So you would just pass this in as like a developer message. And then you have your user message, and then you have start assistant. And then the output has these things called channels, which are pretty cool. So they noticed, a lot of these models, we kind of break down their capability into reasoning or maybe some commentary, and then there's a final answer at the end. So the way they break this down is in the output, they'll have different channels. So let's go back to that like color coded one. So you can see the user message is what is the weather in San Francisco. It starts with assistant, and then it first outputs a channel called analysis. And then this is the LLM thinking through what it's about to respond. So these are like the think tokens. User asks, what's the weather in SF? We need to use a lookup weather tool. And then they'll start the assistant message. And then it says, this will be the LLM's commentary. There's these constraints that you can put in, constraint tokens. So this is how they do like structured output. So constrain JSON, then the message that came out, and then another channel for analysis. The weather in San Francisco is sunny. I can answer. So it's still like thinking through its answer. And then finally, assistant channel final. And then this would be the text that you see that comes out of the model. So it's cool that we have access to all of this stuff from GPT OSS, but you do have to like understand what the different channels are. The libraries take care of parsing from this raw kind of like HTML looking format to a more structured JSON thing, but I think it's good for you to understand that like at the lowest level, this is just text in, text out. And this actually bit us while we were training is why I'm going into such deep detail into this. So while we were training, I posted on Twitter just like a quick picture of our loss curve, trying to promote this event. You guys might have seen it from this, but I said, this is what our training loss curve looks like. And actually the maintainer of Axolotl replied. Axolotl is a really cool fine-tuning library, and he's got a bunch of experience tweaking these hyperparameters, et cetera. And he's like, hey, your training loss looks pretty high. Do you want to look into it? So we spent a late night just like scanning all of our hyperparameters, making sure mine matched his, talking through what it could be. And one of the big things that we found was in our data loader, by default, the apply chat template function puts reasoning medium in. And this means it's going to have some reasoning before it responds. And none of our data had any reasoning in it. It was just going straight from like generate a song as if by Eminem to the lyrics. And so as we were loading the data, we actually changed it to be reasoning low, and then needed to make sure during inference you also pass in reasoning low if you just want to go from like prompt to response. And that's something kind of like sneaky under the hood that you might not think of. And if you think of like the loss at the very start, if it's outputting reasoning tokens by default and you're training it not to, the loss is going to be really high when you start. One side note is I do find it a little annoying that they put the reasoning in the system message. I feel like that would have been better suited in one of these later messages, because then it's kind of like been pre-trained to have that as a part of your ChatGPT large language model by OpenAI. It just feels like it should be separate, but that's kind of a side note. So the way that we did that is just when you're loading and tokenizing your data, you can pass in reasoning effort in here. And then you also need to make sure that that lines up with what you're passing in to your downstream inference engine, because I spent like a whole training cycle using reasoning none, because I thought that would be the lowest level of reasoning. And in fact, it's low. And then I deployed that model, tried to hit it, and it was like, we only support low, medium, or high. So those are the three values that you can throw in there. Figured I'd save you some training cycles from doing that. The other just like intuitive reason why our loss is really high at the start is kind of the motivating example of this fine tune is like for that very first epic, or the very first couple times it's going through the backwards pass, it's going to be refusing all of the answers. So it's not even going to be close to the lyrics that were coming out. So any questions on that so far?
And we just got one from Aditya. Is the Harmony format especially recommended for agentic use cases only? Can we skip it for non-agentic fine-tuning?
Yeah, I would say a lot of those tokens in there are special for the agentic type use cases. And so when you're fine-tuning, I just like be sure that you're looking at what tokens are actually being put in when you call your apply chat template function. We even want to put this in Oxen as like, since we're tokenizing all the data to compute the cost before you kick off a fine tune, we're just going to put that data in there so you can see and make sure that the underlying tokens are what you want. But I'd say you can drop a lot of them if you're not doing agentic use cases. Cool. So how did the training runs go? Let's dive into it. These were the hyperparameters we settled on for PEFT. Did a few experiments with lower LoRa rank and alpha, and it just wasn't learning very well. Calculated like the max sequence length we had in these rap lyrics was around 3,000 tokens, so just cut it off at 4096 to make it a bit more efficient. We did bump the learning rate down a little bit so that it was a slower burn, but can hopefully get to a better spot. And then trained it on 2 epics of this 50-50 split of explicit and non-explicit data. And I'd say the main takeaway from the LoRa experiments is it just has a hard time learning the task here. So you'll see that it quickly drops to around 3, but if you're familiar with any of these other fine tunes, you can pretty quickly get under like 2 or 1 or sub 1 for a lot of these tasks in your loss. And then the mean token accuracy kind of just hovered around 50%, and I couldn't really get it to go above that as much as I tweaked the hyperparameters for LoRa. And I thought this was an interesting tweet from this Ben character here who calls out fine-tuning setup for GPT OSS is kind of a mess. He calls out the no Triton kernels for the backwards pass. And if you want to do any serious fine-tuning other than LoRa slop, you'll need these kernels. You don't need them if you're training in BF16, but I think the sentiment of LoRa's don't work as well as fine-tunes for something when you're trying to like completely teach it a new behavior. We definitely saw that with these training curves. So I did kick off a more full fine-tune of all of the weights. And you can see the difference between that and the LoRa one. So we're able to get past that 3 mark and then start trending down into the single digits. And then the mean token accuracy starts getting above that 50% line. So I feel like these two graphs are really illustrative of this was with LoRa, and then this was with a full parameter fine tune. I think this one's actually still running, so we'll check in on it at the end to see how it did. Daniel asks, what's the cost of fine-tuning the 20B versus the 120B? It depends on what GPUs you're running it on, and then whether you're doing a full parameter fine-tune versus a LoRa. And the full parameter fine-tune, you need 8 by H100s. And so this run here took about 30 or 40 bucks for those, around 4,600 examples for the 20B model. The 120B for a LoRa, you can also run on 8 by H100, so it would be a little more expensive because it would take longer, but I still think it would be in the sub 100 range. Haven't done any experiments with the full fine tune on the 120B yet, so can keep you posted, but sub $100. And for smaller data sets, we can get down into the like 10s or 20s. The next experiment I ran, yeah, so it takes an hour or two. Yeah, that's about right. The next experiment that I ran was, okay, let's just see like if this was a GPT OSS thing. And so I just took Llama 3.2 1B and look how fast this thing starts to cruise down the loss curve and get up the mean token accuracy. I think this one, just from like a rate of learning, went way faster on this task, and I think landed at a higher spot. Yeah, around like 80 or almost 90%, and this thing didn't get above 75. So really telling that they did spend a decent amount of time post-training this thing, post-training GPT OSS to not have certain behaviors. And I think those experiments are telling. And if you read the system card, again, they say, with our adversarial training, we simulate an adversary who's technical and has access to strong post-training infrastructure and ML knowledge. And so they were, in their post-training, like making sure that you can't post-train it too far out of distribution. So I thought that was an interesting takeaway, and that some of the Llama models don't have that behavior. So depending on what you're fine-tuning this for, that might be something you want to take into consideration. And then the final thing that I want to go over is like some of the deployment gotchas. So once you finish the training, journey's not complete. Now you have to get this thing into production. And there's kind of 2 options that are most popular out there. There's VLLM and there's SGLang. Unfortunately, both of them are missing features as of right now. The main feature that we needed to deploy these things, or I guess, wanted to deploy these things is the ability to merge the LoRa in at runtime. And usually that's just like a flag that you set when you spin up VLLM, but it's not supported for GPT OSS right now. So what we needed to do was merge the model weights before you do the deploy, which isn't ideal depending on your setup, because the ideal setup is like if you have multiple fine tunes and then these small LoRa weights, you can download the full base weights to whatever machine you're running it on, and then just download the LoRa weights and like load that at runtime. Instead, we had to load it all, do this merge and unload, and then save the weights back to disk, and then deploy that. And that's like a much bigger deploy than just the LoRa itself. So that's just something to watch out for if you are running this in VLM or SGLang. But other than that, it's pretty straightforward. Once you have the weights merged, you can just do like VLM serve path to those weights, and then any other parameters that you want to pass in. VLM also doesn't fully support all of the Harmony format yet. So this is a good tweet that had a feature breakdown of what VLM supports and what it doesn't support yet. So there's a couple modes of operation here. If you've ever wired up some of these APIs, there's streaming responses. So like the way that you can get word by word into your chat interface. And then there's like a full chat completion where you send it and it sends all of the text back. So in some cases, the streaming works with structured output. A lot of them, or a lot of VLM doesn't work with the built-in tools or MCP servers or function calling with the streaming responses yet, or the chat completions API. So if you're just using the new response API, it does work with those ones, but just watch out if you're using different APIs have different levels of support right now. And that's just like going back to having a keen eye to look at the GitHub repositories for VLM and see if they dropped a new release that'll support your use case. Luckily, that's some of the stuff that we do behind the scenes at Oxen. So we deploy this and check all of those versions and make fine-tuning and deployment really easy for you. But if you want to do it yourself, these are good things to look out for. So next up, we are planning on supporting the 120B model. We'll start with the LoRa because that just works on a smaller cluster of GPUs. We'll have to do some experimentation for the full fine-tuning, and then want to add support for that Harmony format, tool calling, and like a full chat messages history. Because if you remember, we just have like the simple prompt and response, which is good for some use cases, but for others, you'll want like a more verbose input and output. So that's some of the stuff that we're working on next, but with keeping in mind that VLM doesn't even support those things yet. So we'll kind of be waiting until the deployment supports it until we make the fine tune support it. Cool. So that's all I had. Any questions? These fine tunes are still running, so I wish I could show you more in depth. We'll see if this one gets above and into the 90%. This is like the full fine tune of the 20B. So in the follow-up blog post, I'll show some inputs and outputs of that. And then, yeah, Daniel, this is a public repo on the Oxen platform. If you want to like take a look at the data, grab it yourself. There's a few different experiments I'm doing here, notebooks that I have to clean the data, and I even have data from a bunch of different artists in here. So that might be fun to play around with if we want a larger data set. We have another question if Oxen supports RL like PPO. Not right now, but we have experimented with that in one cool thing that you can do in Oxen is if you have notebooks, you can launch them on GPUs. So like I could spin this notebook up on an H100 with up to 64 cores and 64 gigs of memory. So I have done some RL workloads just in a notebook itself, namely for code completion type tasks. And then I actually, as the reward function for GRPO, run the code, run the unit tests, and have that be the feedback. So that's kind of a fun way to roll it yourself. And then kind of what we do on the back end is we're developing all of these fine-tuning scripts in notebooks on GPUs, and then we're going to be rolling out support for them in the one-click format. So that's how we'll go forward and like support some of these RL workloads. Cool. Well, I'll kill this recording if you guys are watching online. Thanks, and feel free to share it with your friends. And if you're live here, we can kill the recording and do any other questions and answers. Thanks, y'all.